Okay.
Yeah. Well, it's the same thing as he's more than the same thing as tracing out the webcam, right? Yeah, he's trying to do and that trace will also generate your density. Like he's just telling you initial conversation. Yeah. I was just wondering what what you can in general, but in this case you get like coincidentally the time you know where the report is supposed to be. Yes, this is the statement is that this would be
Independent answer is going to take at least another year.
As loud as I thought it would be. All right, welcome back, everyone. Is it 2 o'clock? So ready to continue the program with Tom Faulkner. Tell us more about operator algebras.
Okay. All right, so I'm just going to start where I finished last time. So we were talking about the KMS condition in quantum field theory. We were trying to identify what the modular operator is for the wedge algebra. So the wedge algebra is associated to the Rindler wedge. The operator's in here. I'll call that A of omega or A of W. So we have to check various conditions to see, and we had a conjecture for what the modular flow would be, and it's just boosts. And so we have to check various conditions. The first is that the vacuum or the state restricted to this algebra is invariant. That's clear because it's a boost. And the other thing is that it should take the algebra to itself, which it does because it holds fixed the Rindler wedge. And then finally, the KMS condition had to be true. And we could check the KMS condition by analytically continuing correlation functions. And this is where we use the spectrum condition. So the spectrum condition implies certain analyticity properties for correlation functions. In particular, if we think about just inserting local operators, we can insert some operators. So now I'm including the Euclidean time direction, imaginary time. And to guarantee the correct ordering in this correlation function, we put a little I epsilon here. So these operators come first. These are the 1 operators. These are the 2 operators. We can boost the 2 operators. We can also analytically continue the boost and go around 2 pi. When we do that, keeping track of the I epsilon prescription, you get back to yourself except up to a different ordering in the correlation function. And that's exactly the KMS condition. There's a few things I should have said last time to justify this. So one thing you have to keep track of is this I epsilon, right? And the issue with I epsilon is you might, when operators come close to each other or become light-like separated from each other, then you might hitch branch cuts, and that precludes you from analytically continuing, or it means the function is no longer analytic at that point. So you have to worry about whether operators will become light-like separated. As we move the operators around here, you might worry over here, I'm changing the time ordering. I'm changing the I epsilon prescription. However, that's totally fine because all the 1 operators are space-like separated from the 2 operators. So you don't hit any branch cuts, and you can actually analytically continue further and go all the way around. Okay, so that's the full argument. And so that's the KMS condition. And so that means the conclusion, let's go over here, is that by the theorem that I quoted for you, is that there's some state in the Hilbert space whose such that the modular operator, delta psi, the IS, is this boost, right, or the generator of this boost. So the generator of this boost I'll call K. K generates boost. Because I had to go around 2 pi and not 1, which is usually how you state the KMS condition, there's an extra 2 pi in this identification. Like that. Okay. One issue is we actually haven't identified psi as the vacuum state. So is psi the vacuum state? It's not hard to see that because the state, when reduced to the Rindler wedge, is the same, that means that it has to be the vacuum state up to a unitary on the commutant, right? Because the unitary will cancel when I compute expectation values of any operator in the wedge. And so how do we fix this? How do we fix u prime? Well, the answer is the modular conjugation operator, which I haven't talked about. We can proceed in a very similar way. We just guess what it is, and we just check that it satisfies all the properties. And so a natural guess is the CRT operator in quantum field theory. So CRT is the usual, well, it's CPT is the usual symmetry of a quantum field theory that you prove always exists and leaves invariant the vacuum. I can switch parity for just a reflection. Can always do that. And so I pick R to just reflect across this axis here. Then you can check that CRT is anti-linear, anti-unitary, right, because of the time reversal. And because of how R acted, and because of how T acts, you can also check that this is true. So it takes the algebra to its commutant. Technically, it's this. And you can also, you also know that CRT holds fixed the vacuum, okay? So as long as CRT is a candidate for a modular operator, that will actually uniquely fix the modular operator. So this will fix J to be CRT and U prime to be 1. Right, so that fixes the unitary degree, freedom here because J has to hold fixed psi. Right. Now there's one more step that I didn't say. What characterizes the CRT as an as a possible modular conjugation operator? It turns out that there is a paper that discusses this by Araki. Characterize modular conjugation operators. And it turns out that you need one more thing, which is often called wedge reflection positivity. So reflection positivity is some constraint on correlation functions in Euclidean time where you reflect across some axis that you pick. Wedge reflection positivity is just related to a reflection in the x direction where you do this in Euclidean as well. Okay, so it has a consequence also for correlation functions in real time, and you can check that the Whiteman axioms imply that this is true. Okay. So I'm not going to go into many more details, but that's the full argument. Okay, good. So this thing that I've told you about has a name. It's the Bisignano-Wickman theorem. It was studied before we understood physically what was going on. So physically, usually the story is you think about the Rindler wedge as being described by a family of uniformly accelerating observers. Those uniformly accelerating observers never see the region over here. it holds the algebra fixed. Yeah, that's sometimes a confusion, but it does map operators to different operators. So yeah, that's a different thing. Yeah, yeah. What you're talking about is called the centralizer, and that's different. Okay. Okay. So one thing. Let's start with the following observation. So we you know in the right algebra. So this is the commutant. We're also just going to identify it as the left algebra and give some arguments for that. So if we think about the right algebra, okay, so we have these are quantum fields on the right wedge. Okay, so the quantum fields over here, right? And they commute with the left Hamiltonian. Yes, question. It's not, no. It's a representation of that algebra on this extended Hilbert space, which includes the L2 of R. Yeah. If you like, I should have also said that here. This is really tensor 1, which is also a representation on that Hilbert space. Yeah. It's just a different one. Okay. But yeah, it's different operators to the input operator. It's a different operator. Okay, so A0 on the right are our quantum fields over here. They commute with the Hamiltonian on the left. But what if I extended these operators here? So I could even think about A0 of L, right? Those operators, which is not the same as those operators, commute with the left Hamiltonian. So it's reasonable to think of them as being dressed to the right boundary. Okay, and so what do I really mean by that? I mean that they take reference their time, which is given by the right boundary time. Okay, so for example, let me try to. Okay, let me just say one thing, and then I'll say a little bit more about this. So, but note that this representation of A0 left, if I take the left Hamiltonian and I act on this representation, because of this time operator here, it will, and the canonical commutation relations between T and HL, like this, it will actually have an action on this thing, and you can do the math, and you find that it's just modular flow with some rescaling of that operator. So H left doesn't commute with these operators on the left. In fact, it just generates time flow. So that suggests that those operators are let me write it like this, pi of A0 left, are addressed to the left boundary so that when you act with the Hamiltonian, they actually see that left Hamiltonian and they don't commute with it. Okay, so that's kind of the rough idea. I can be a little bit more precise. So if we think about this time shift mode, okay, so here I have this natural slice through here, but now I have some time shift, and you should really think of this as being some operate. So this is some wave function, right? So there's strong fluctuations here. So I can't really say that there's any fixed time. But let's sort of work in one part of the wave function where the time is approximately fixed, and then this would be the picture. So the right dressed operators are based on this time here. So you're sort of dressing over here, and like this. And they're based on knowing this time. Now, if I want to dress them to the left, I have to make up for this time shift here. And so that's what this pi does. And so effectively, you're working now on a boosted slice like this, where now this slice looks like this over here, and now this is t hat. Right. So this is what pi does. And so now things dressed to the left are dressed like this. Okay. So good. Now the main punchline is that this algebra, this cross product algebra, is not a type 3 anymore. It's type 2 infinity. Okay? Oopsie. Sorry. Oh no. Yeah, it's because I haven't included this pi. And so one way to sort of argue for it is the fact that it commutes with the left Hamiltonian. So if I try to change the time on the left, it doesn't do anything to this operator. Right, so in terms of the time, like the dressing in particular with respect to this sort of time fluctuation, it's dressed to the right. Yeah. Yes, yeah.
When you draw this picture here, so this pi is anchored to the left, but then if you just have a naught left and it's not, is that like so when you act with h left?
Oh, yeah, I didn't really mean to, yeah, okay, let me just draw it like that. It doesn't really, you can anchor it to anywhere, it's just with reference to this time.
I just mean like pi of a naught compared with a naught itself.
Ah, yeah, I think you should try to understand what this picture is trying to say. This is like a0 on the left, say. This is a on the left, or some operator a that's dressed out here. And then this is pi of a0 on the left. Right, these kinds of operators. Yeah, so I think that's this. You should try to understand this picture. Yeah, maybe you should think about it offline yourself. I encourage. Okay, so yeah, so I was saying AR is a type 2 infinity factor. So why? Well, the way you show this is by producing a trace. AR is a type 2 infinity factor. Well, at least that gives evidence by producing a trace. You still need to show it's a factor, but then you can just quote Takasaki's original paper on these subjects, and Cohen's and others. Okay. All right. So there exists a trace. So the interesting thing about this trace is, notice that on the right, A0 of R, I guess tensor 1, is a subalgebra of AR, okay? So this is type 3, it doesn't have a trace, okay? But I'm claiming that this has a trace. Can't I just take the trace on this and restrict it to this? Question? You can't, no, because this trace is one of these unbounded traces. So it could blow up on many things. In fact, it will blow up on all of these. So you won't even be able to define it on this guy. So yeah. And this also illustrates the fact that it's sometimes confusing, which is that you can have inclusions of any types here. They don't have to increase the type or anything like that. All of these are subalgebras of a type 1 factor, which is just B of H of the full Hilbert space. Okay, so there's a trace. And so what is this trace? So let me just write it down. So the way to write it, or one way to write it, is we're always going to take expectation values in this sort of defining state for which the modular operator is defined. But on the L2 of R, I'm going to introduce a delta function state, right? One of these bad states that you're not really allowed to talk about in quantum mechanics, and just sandwich it between these two, or something like that. I guess you understand what I mean. Now, the fact that this is a bad state to put here is related to the fact that this is an unbounded object that will only sort of be defined as long as the stuff that I put in here sort of deals with the fact that this is a delta function normalized state, okay? So you have to put in sufficiently smooth functions of the energy, or well-behaved functions of the energy, so that this is the case. And so that's what we're going to do now. So there's A hat here. So A hat is in this guy. So let me do that. So, and then I'm going to try to convince you that it's a trace. Yeah, I do. Last lecture. Okay, so let's think about elements in the algebra. It's generated by functions that I described over here. Or somewhere here, yeah. So it's generated by functions. This is in A0 of R. And then I need functions of HL, so I'm just going to do some Fourier analysis. Like that. So that is in A. And then I'm going to pick A of S to be an entire function of an entire function between C and the algebra. All right, so it's sort of an algebra valued function that's entire analytic in the entire complex plane. So these are well-behaved function operators. They're not all possible operators. But you can always approximate an operator by one of them. And so then I'll take another one. Same thing. And then to see that it's a trace, we just have to calculate this thing. And so there's a few steps here I'm just going to drop in lieu of time. But it's not hard to arrive just to take those expressions, use the fact that you have these delta function states here to evaluate HL. We'll shift those delta function states and so forth. And you just get an integral over one of the S's. So there's two S integrals, but it collapses to one S integral over the following correlation function. A, which form do I want it in? Yeah, minus S plus I beta delta 1 plus IS over beta B of S. Oh my God. I don't know why I put it there. So this is just a correlation function in the original quantum field theory and integrated over these things. Okay, so there's some integral. It's integral over R, but I can analytically continue that integral just because of this entirety assumption on these functions. But now the point is that we're going to use the KMS condition. So the KMS condition is key here. In some sense, what we're doing by introducing this extra mode is reweighting the KMS condition so that it becomes tracial and it becomes exactly commuting. So the operators can exactly commute without having to introduce a modular operator. So, uh-oh, that's bad. Okay, and so now what you do is you just use the KMS condition, KSM, KMS condition, yeah, so you use the KMS condition to rewrite this as omega B of S, yes, minus S. So the KMS condition will get rid of this delta. That's all it's doing, and it will commute the operators like this, right? But then to get back to something that looks like this, I just then analytically continue this integral, which I'm allowed to do because I had this constraint on these operators. And so you get, quickly, you get that this, after shifting the contour, is just S phi beta which you'll see is similar. Sorry, I just changed the, yeah. If I just put S to minus S, you'll see that this is the same form as this. The only thing that I've switched is the A and the B label. Okay, so that means this is equal to tau of BA. And so it is a trace. Okay. Okay. So a few minutes. Okay. Now we have a trace. Another interesting thing you could do with a trace, which is what was done in those papers that I mentioned, is you can compute entropies. Right. So what are entropies? Well, I can just define the entropy, which is sometimes called the type 2 entropy of some state, just using the relative entropy. And so I'm just going to take the state and compare it to this special state, this tracial state. And the motivation for this, we actually talked about, someone asked about it in a previous lecture. In type 1, you can write the relative entropy as the relative entropy, sorry, the von Neumann entropy as minus the relative entropy comparing to a maximally mixed state. This is a tracial state in type 1. 1k, this is the dimension of that Hilbert space. And so up to a constant, this is true. So there's some constant here, but we can't fix that constant. Actually, there's a reason you can't ever fix that constant using type 2 infinity. This trace, you can always rescale. There's nothing to fix its normalization. So there's nothing to fix the overall number of this entropy, but up to a number which is state independent, that's the entropy. So in other words, in type 2 settings, we can always define entropy differences. They're always well defined, but yeah, so in type 3 you can't. Type 2, entropy differences, well defined. And so now there's an entropy, and you can try to compute that entropy in certain settings and compare it to what we expect. And that's also what this paper did, and there's a lot to say about that. Let me just summarize the result. If you think about a special class of states, which are called semi-classical in that work, where I write my total state on the Hilbert space as some state on the quantum field theory Hilbert space times some function which has broad energy fluctuations. As epsilon goes to 0. So in some sense, we're trying to get back to the setting where we're in the canonical ensemble. But we're not taking any limits. But we have some energy fluctuations, and this is like 1 over epsilon to the half. And so you scale that out, and it becomes very broad as epsilon goes to 0. And in this limit, the time fluctuations become small as well. And so you might expect to be able to identify the entropy, type 2 entropy in that setting with other entropies we've defined in this setting. And indeed, in that limit, you find the type 2 entropy can be written as a relative entropy between the state of interest and the vacuum state plus some expectation value of the energy minus some entropy associated to the fluctuations of the entropy. And furthermore, you can argue that you follow an argument by Aaron Wall a long time ago that argued that the relative entropy was equal to generalized entropy differences along the horizon. And you can identify this as the entropy, generalized entropy here, say I, generalized entropy at some later time. And so if you then identify this with a generalized entropy at later time, which makes sense because at very late time, all states look the same. So it's sort of state independent. It's just related to the fluctuations of the energy. Then you can identify the type 2 entropy up to a constant as just the generalized entropy. Right. And that constant is state independent. So this is, yeah, sort of powerful result. Okay, and there I'm done.
of the time, both the time on the left boundary and the time on the right boundary. We should go take our break and save questions there. Let's thank Tom one more time for this great lecture series.